So we're going to hear from Wouter and Alan.
That's the intro. Great.
Yes.
All right. So welcome everyone. So this is the second tutorial of the reinforcement learning theory semester. And this one will be about online learning and bandits. It will be in two parts, and I will do the first part, and Alan Malek will do the second part. All right, so let me try to navigate all these things. Okay, so what's the purpose of this tutorial? So first of all, we'd like to share with all the people, there are at least 200 of you, the tools that we need for reinforcement learning. So we'll build up some of those here. And then we'll also have some exploration of surrounding viewpoints, slightly different problems, slightly different methods, right? And another purpose is maybe to make sure that we all speak the same language, understand each other's perspective, sort of create a shared culture. So I hope that will work. Let's see. So what's it all about? So the goal is to make interactive decision-making systems or sequential decision-making systems that can operate in an unknown environment. Let's see, Java is completely frozen. Is it me or can everybody else hear me?
I can hear you, Wouter.
Okay, great. So we're trying to design decision-making systems for unknown environments. And we would like these systems to get as much reward as possible in a large variety of environments. Okay, and I'll make a distinction that is maybe the main distinction in this line of work, which is what sort of environments are we assuming to operate in? So in reinforcement learning, I think the main point is that you imagine that your actions affect the future state. So that makes that you have to do planning and sort of thinking ahead. Then in Bandits, which is in some sense a simpler problem, you assume that your action observes what you see, but not what happens afterward. And then full information online learning, which is this part of the tutorial, is even simpler. You basically think that your actions really don't affect anything, or maybe they only make a certain reward for you. But there's observations, you observe everything, and the future doesn't care about what you did, right? So in that sense, it's a much restrained problem. In some sense, you assume less. You need to assume less to work in this setting. Okay, so as I said, there will be two parts, the full information part and the bandits part. And for the full information part, I want to talk about two basic problems, namely online convex optimization and the experts problem. Then I would like to go a little bit beyond the basics and look at two sort of slightly advanced, interesting extensions, namely follow the regularized leader and mirror descent. And I want to look at online quadratic optimization, which is sort of a special problem where you can have efficient learners. Then I would like to illustrate what all these things are good for with a couple of applications, standard optimization, stochastic optimization, and solving games. And then we'll see some extensions at the very end. Okay, so let's start with the two basic problems. Okay, so maybe one thing to say before we start. I'm a very pessimistic person. This is the default in online learning. So I'll always talk about losses and not rewards, but you can just put a minus sign there if you want. And we're going to think of our environment as something that we don't want to make any assumptions about. So we're basically going to give it some adversary control over all the environment's decisions. All right, so let's introduce the first problem, which is online convex optimization. So it's a certain interaction in which we have to operate. And to simplify things, let's say this interaction will go on for t many rounds. And there is given up front some convex space, let's call it U, in d dimension, if you want, think of a ball that we call actions. All right, so we'll go interact with the environment for t many rounds. Each round, we have to pick an action. We are the learner. So we pick some action WT from our action space. And then the opponent or the adversary or the environment decides how good all the actions that we have actually were. So to make that sort of formal, we say the adversary picks a function that for each action says how good it is in the form of a loss. So that function, we call it FT. So that decides the quality of all the actions. So that means that our loss at that point is FT of WT. And we assume, and that's the full information assumption here, that this function FT is available to us as we like. So we basically know everything about it after it's chosen by the environment. Okay, in some sense, it is a bit abstract. There is no predictions, there's no outcomes, no nothing. It's just actions and how good they were. But when you're building tools, I think that's a useful thing to have. You don't need to make many assumptions. You can fit many problems in this framework. Okay, so that's what we have to do. Now, let's say, when are we doing a good job? So we'd like to get small loss. And it's not really possible to get small loss. But I guess the next best thing is to say, well, if it was possible to get small loss, I want small loss. So what we're going to do is control something called the regret, which is the amount of loss that we got, which is the sum of the FTWT, minus the amount of loss that we could have got if we had played the best action for all the rounds every round. So we think of that as the loss that we could have got if we know a good action, and we look at how much more loss we have. So that's the regret, and that's the quantity that we're trying to keep small. So we're designing a learner, so that's a way to pick the WTs, and we will prove that it makes sure that the regret is not big. And then we'll look, for example, at is this learner efficient? Because it has to be an algorithm that we can actually run. Okay, so let's think a bit about how to build such learners. So if you want to be like the best point for all the data, then in some sense you are chasing this best point. You don't know the best point up front, it's only decided at the very end, but you get some information about it and you sort of have to get there, right? But if you play at any point the best point so far, then it turns out you're jumping around quite a lot. In some sense, you're overfitting, and that's not a good idea. So the first sort of design principle that we see is to say, okay, let's regularize a little bit. And there are two ways that you can do that. You can say, well, I should maybe not play actions that are quite extreme. So maybe I should penalize those. And for the connoisseurs, that's the FTRL style of regularization. And the other thing you can do is you say, well, maybe I should play iterates, and I should make sure that they don't move too much. That's the mirror descent style of regularization. So we will see examples of both, and in some sense, they're not always quite the same, but they're very similar. So we'll just think they are equivalent. Okay, with that principle in mind, let's look at our first algorithm. It's called online gradient descent. And let's, for simplicity, assume that the origin is in our action space U. The algorithm has one parameter, which is a learning rate, that we call eta, some positive number that we will set later. And then the algorithm will do the following. So in the first round, it has not seen anything yet. It will play the origin. And then it will update when it gets to see such a loss function as follows. So it takes the old point. Let's see if I point with the mouse. Hope you can see it. It takes the old iterate. It says, let's compute the gradient of the loss function at the point that we played. So the gradient is the direction where things get higher. So that's where the losses get higher. So we want to get away from that. So we take a step away from the higher losses. So we go in the direction of smaller losses with a step size that is controlled by this learning rate parameter eta. Okay, so that's in itself a gradient descent step. And we have to be a bit careful that we might go outside of our action set U. So if that happens, we project back onto U in Euclidean distance. Okay, so the way that looks is you have your action space U, you have your iterate WT, you update by taking a gradient step, and if you went outside U, you project back onto U.
Wouter, this is Ambuj. Sorry to interrupt. There's a question about the protocol itself. Who observes what? What does the adversary know when they're playing the functions, and what does the player know when they're playing the points?
All right, so Ambush, I'm curious where you see this question because I don't.
This is coming from Discord. This Discord.
Okay. So let me just go back to the protocol. So the interaction is happening sequentially t many rounds, and basically I wrote it explicitly, but it's what every time you meet one of these lines, and either the learner or the adversary has to make a choice, everything that happened before is observed. Okay, so if you have to make your iterate, your action, you know what happened in terms of the W's and the F's in all the previous rounds. And the F function of the adversary even knows the WT. So that's completely evil, if you want. But it turns out we can deal with that. So there's no information that's hidden to anyone. Okay, I hope that helps there. Okay, so this is the algorithm. Let's see what we can prove about it. So here I repeat the algorithm, and we will have to make a few assumptions. So the standard assumption in this line of work is to assume boundedness. So we will assume that the domain, the set U, is bounded in norm by a constant D, and that the gradients are also bounded in norm by a constant big G. Okay, and then we can show that the regret, which is the difference of our loss minus the loss of the best point in hindsight, is bounded by something that scales with D and 1 over the learning rate, and something that scales with T and G and the learning rate itself. Okay, and then it turns out if you look at this and optimize the learning rate, you would like to tune it as D over G square root T. And if you plug that in, you get the classical gradient descent bound, which is that the regret is at most D times G times square root T. Okay, and what this means is that our regret is sublinear. So the overhead that we are getting for not knowing this optimal point, but learning it, the overhead is square root T, which means that per round, this overhead is going to 0. Right, so we're successful at learning in this task. Okay, let's have a look at the proof. I just want to go over 1 or 2 proofs in this tutorial just to show you what they're like. If you don't really catch everything, that's fine. The slides will be available and the rest of the tutorial will not depend on it. But let's look at it a little bit. So the regret was the sum of our losses minus the sum of this optimal point in hindsight. And one thing that we can do is we can say, I know that these functions are convex, so I can bound them by the tangent bound in the point that we played. Okay. And then we're going to do some analysis about, well, to somewhat be a mysterious thing, but let's look what happens. So we're going to look at, let U be this a good point at the end. So we're going to look how far is our iterate from this U in squared Euclidean norm. Okay, what do we know about it? Well, our iterate is the projection of the gradient step from the last point. Okay, good. So we're looking at the difference between a projected point and this good point U. right? So one thing we can do is we can throw away the projection. And there is a thing called the Pythagorean theorem that says at that point, the distance only becomes larger. So we have the distance of our updated iterate to u. And then we can work out the quadratic and write it as the distance from the previous iterate minus the cross term plus the offset all squared. Okay, and if we reorganize that a little bit, we see that at this point, oops, at this point we have the linearized regret. So we can put that to the left and say the linearized regret is at most the distance of the old iterate minus the distance of the new iterate, all divided by 2 eta, plus the square of the gradient times eta over 2. Okay, so the regret in one round is bounded by this linearized regret, is bounded by this 2 terms. There is a difference in norms, and there is a gradient term. Okay, so let's put that in. Regret bounded by linearized regret, bounded by sum of gradient differences and sum of gradient terms, sorry, norm differences. And if you look here at these norm differences, you see that they're all offset by 1 time index. So that means that they're telescoping to the first minus the last. And we can even throw away the last because it's a negative contribution. So we get just the first, which is just the norm of u because we start at the origin. And this we sum. And then we can use the bounds that we had on the norm of u and the norm of the gradients to have a d squared over 2 eta plus eta over 2 times dg squared. Right, so that was the result that we said we wanted to show. Okay. So now we proved, for example, this bound. So we now have a method based on gradient descent for operating in this online convex optimization world. And we have a regret bound that says it's working. Okay, so the next step is to ask, is it a good bound? So you can look at it. It has 3 factors. Scaling with G and D, that's completely natural. They just scale everything, including the regret. So those we believe, but maybe the square root T we should investigate a little bit. Okay, so there is a theorem that says any algorithm that operates in this online convex optimization protocol needs to have a regret of order square root T. So that means you can't really improve this. So let me just give you a slight flavor of how that works. Basically, what you're doing is you say it already works this lower bound in 1 dimension. So we can assume that our set is some interval, say -1, 1. And we can give the losses to be some linear losses with coefficients for simplicity that we make plus or minus 1. Right, so you have your set u, and every round the loss function is either linear with slope 1 or linear with slope -1. Okay, so what does that mean? Well, first of all, your algorithm has expected loss 0 because the coefficients are on average 0. Good. And the best action is the best action fit to all the data. So that doesn't have expected loss 0 because it's actually random. But you can see that the best action will either be on the far left or on the far right. And as a result, it will make an absolute value appear. Okay, so the expected loss of the best action is minus the expectation of the absolute value of the sum of the coefficients. Okay, so that's a sum of Rademakers, which is roughly, you can think of it as a normal random variable. And the expectation of such a thing by, for example, central limit theorem type reasoning is roughly square root T. So that means that the expected regret, which is the expectation of our loss minus the expectation of the best, is actually square root T, lower bound, right? And that means that it's not only true in expectation, but it has to work for at least one sequence to be that high. Okay. So what did we have so far? So we have an adversarial result. No matter how the loss functions are chosen, we can learn in this context. So that's super strong. If we think about the proof, it sort of tells us, well, we said convex, but it's really only linear is the hard case. So we were analyzing linear things by linearizing all the time. But we managed to get matching lower bound. So we completely closed the problem there. And just as a side note, actually this style of thinking is quite successful in practice. And if you dig a little bit and look at what's being done in deep learning, which is driving all the cool applications of machine learning and AI these days, they all use at some point optimization to learn the parameters of the network. And typically that's done with, for example, TensorFlow. And if you look at the optimizer, that's AdaGrad, which is the big brother, some bells and whistles added to online gradient descent. Okay, so the objective there is not convex, but the methods are successful anyway. Oh, a question here. Proof reveals it is really about linear losses. Yeah, so we did a step in the proof to say the difference in losses is upper bounded by the linearization. And that step is tied if the losses were linear. And it's lossy if in any other case, right? So in that sense, the linear losses are the hardest case for the upper bound. And you saw that the lower bound was also based on linear losses. And the other question is, yes, how arbitrary is arbitrary? The loss functions are arbitrary. They can even be chosen with our W in mind. One way to think about it is that it's possible to give the learner a large loss by just setting the loss of WT to be very big. But it's not possible to keep on doing that and not make all the other actions also bad. So if the opponent wants to give a large loss to the learner, it will give a large loss to everyone. And then the difference between the learner and the best action is still small.
Related to that, Wouter, there was a question on Discord as to why the best in hindsight is a single point and not a sequence of points.
Let's wait until the extensions before we answer that. It's a good question. We'll get to it. Okay, so now I want to get to the second problem, which is somewhat related, slightly different. It has many names. For example, decision theoretic online learning, the expert setting or the hedge setting, prediction with expert advice. All these things mean almost the same, but slightly different things. So I had to pick one. I chose prediction with expert advice because it's common, even though it's arguably wrong. But okay, people started calling this problem that. So what's happening here? We have a similar game of length T rounds, but now we say we have K many experts. Okay, so what do? We go and iterate for T rounds. And every round we choose a distribution. So that's again a WT. It's now from the probability simplex on K actions, right? So this is a vector that sums to 1, all non-negative. Okay, then the opponent says, how good are each of these experts by revealing a loss vector, which is bounded, let's say in 0, 1. And the loss that we attribute to the learner is the inner product. So that's the, if you want, the expectation, if you sample an expert from these weights of the loss of that expert. Okay, so you can think of this as doing an expectation. In that case, we're analyzing the expected loss. You can also think of this as like splitting maybe a euro and actually getting this average either way. Okay, and the goal is again to control the regret. So we would like to make a learner that chooses these WTs and that has a loss that compares favorably to the loss of the best expert after T rounds. Okay, so what's really different? What's new? What's the same? So let's see if we can already solve this problem with what we did before, right? So the dot loss is linear and hence convex. Great. The gradient is 0 unbounded, and that means that its 2 norm is at most square root k. Okay. And the probability simplex is contained in the unit ball, meaning that the norm of every action is at most 1. Right, so we can in principle apply what we know about online convex optimization and run online gradient descent with d equals 1 and g equals square root k and get square root kt. Good. So is that the best we can do? And of course, I'm asking this because the answer is no, but it's still instructive to think, why not? Where is some slack? I guess the lower bound has to not work in this example. And if you think what the lower bound was doing is it was trying to pick 2 points and give them losses that were as different as possible. And it was able to give them a difference that was scaling with G. But in the simplex, which is where we are working, there are no points that have a loss difference that is as large as square root k. In the ball, yes, but in the simplex, not. So it's actually, simplex is much smaller than the ball. That's one way to think about it. And maybe we can't get as high as square root kt. Okay, and it turns out that there is an algorithm that gets something much better. So that's the second algorithm that I think should be in everybody's toolbox. It's called exponential weights, and sometimes also the Hedge algorithm. And it's designed specifically for this simplex setting. So the way it works is it also has a learning rate. It's playing an element of the simplex, but instead of making these gradient steps, it's doing something else. It's saying, let's make the weight at time t of expert k be proportional to an exponentially down-weighted version of the sum of all the losses of that expert so far, scaled by the learning rate. Right, so we're giving the experts with a very large loss so far a very small weight, and the guys that are doing the best, they are getting the large weights. Okay, and if you like, you can think of this in an incremental version as well. If you do that, you see that the first iterate is always uniform. And if you want to update from the previous iterate, you multiply in one of these exponential factors and renormalize. Okay, so these are two equivalent ways to describe the same algorithm. Okay, so you can also show a regret bound for this algorithm. And the outcome of the process is in some sense similar to what happened for online gradient descent. Now the regret is at most logarithm of k over eta plus t times eta over 8. Right? And you see that if you tune optimally your eta again, you get half t times log k all in a square root. So the dependence on t is more or less the same as before, but now we have a logarithm of k appearing here. Okay. So I want to show you the second proof. It's in some sense a different style of proof. I don't know if that will be obvious to you. Let's just go over it. So if you look at your loss, we can do something that may at first look funny, which is to say, let's approximate that inner product by somehow a log sum exp version. So it's minus log scaled by 1 over eta, linear average of e to the minus eta of the losses. So we would like to approximate linear by log sum exp. That is actually not an upper bound, but if we add this extra overhead term, eta over 8, then it becomes an upper bound. So this is something known as Hoeding's lemma. I'll just import that at this point. So we can express our loss as these funny things, which I think call mixed losses, and then one of these eta over 8 overheads per round. Okay, and then same as before, we're going to find that there is a telescoping going on. So if you look at the sum of these mixed losses and you plug in the definition of the exponential Weigths iterate, which was this e to the minus cumulative loss normalized, then you see that this extra factor for the round t can join with all the factors for the previous rounds and become a ratio of these exponentials with t and t minus 1. Okay, so that means that this whole thing telescopes again to the, I guess the last term, which is here, and the first term where there is nothing in the exponential, so that sums to k, which is here. Okay, and then you see that there is a sum of k things. If we just take, instead of the sum, the minimum, because of the minus, that becomes larger, and then the 1/overs and the logs and the exponentials all cancel, and what remains is that we get the loss of the best guy. Okay, so what we showed is that our loss is bounded by the loss of the best, so the difference between that is the regret, plus logarithm of k over eta, and then this t times eta over 8. Okay, so let's summarize a bit where we are. We saw that in both cases, we're doing this balancing act. Two terms, 1/over a learning rate and a linear in the learning rate term. And you can sort of convince yourself where these terms are coming from. If you have a large set of candidate actions and you make small steps because your learning rate is small, then it takes a long time to get to a good action. So that's what this term is about. The smaller the learning rate, the larger this is. Okay, and then the other term says if you take large steps, then what's happening is you're not able to get to a good point, but you'll constantly be flopping around, in some sense overfitting as you go. And that costs you every round by something that scales with the learning rate itself. Oh, there is a question here. Does the general regret result continue to hold for convex but non-differentiable losses if we replace the gradient by the subgradient? The answer is yes. None of this depends on differentiability. I wrote gradient, but if you do a subgradient, that works fine. You just need the tangent property. That's all we used. Okay, so this perspective on these two bounds, it generates a lot of questions. You can look at all these ingredients and wonder like, okay, is this dependence what we want? Is it optimal? Is there some other things that we would like to have in place? So for example, what if the horizon is not fixed? Can we do something that works at any horizon along the way? What if we don't know the gradient bound? Remember, it was necessary for the tuning of the learning rate. What if we don't want a bound, but the actual gradients? Can we make that happen? What if we don't know the complexity of our model? So that's in this case D. Can we adapt to some good D in some way? So that's sort of advanced stuff for which I would like to refer you to a recent ICML tutorial that's recorded. So you can find answers that to those, well, to that last question in particular. For many of these things, you take the basic analysis that I showed you and you do some extra stuff. So you restart with a doubling trick, you do online decreasing learning rates, yielding something like eta grad or eta hedge. You can learn the learning rate if you don't know that it has to always decrease with a scheme called metagrad. So just wanted to show you all these things to point out that it's quite an active research area where many interesting things are looked at. Okay, so in the rest of the time, I want to do two more things. I want to show you some advanced things in a bit less detail. And then I want to go over a couple of applications. So first advanced thing is maybe the response to some question, namely, what if my domain doesn't look like a ball and it also doesn't look like a simplex? Maybe it's some matrix domain, for example, with some norm constraint like schatten norm or trace norm, nuclear norm. There are lots of things where those type of actions are what you want to think about. Or it could be like a PSD constraint, something. So what do I do in that case? Well, it turns out there is a generalization of the two algorithms that I showed you that might work for you in that case. So they are, again, very similar, but a little bit different sometimes. The first is called follow the regularized leader. And what you do there is you say, my iterate at time t+1 is the point that had the best fit on the linearized losses in the past, so up till now, but you regularize a little bit for how extreme this U is. So you have a regularization function, convex, that penalizes U's that are far away from, let's say, the origin or whatever special point in your space. Okay, and the other scheme is called mirror descent, where you do something similar, except you only look at the optimization of the loss on the last round, and you trade that off with some notion of distance from the previous iterate. So this is, I wrote here B, it has to sort of designate a Bregman divergence. I'm not really explaining what those are, but if you have such a Bregman divergence, you can run mirror descent. Okay, and then if you look at what the examples that we did so far, so for online gradient descent, the regularizer was squared Euclidean, and the Bregman divergence was squared Euclidean distance. And if you look at exponential weights, regularizer was Shannon entropy, and Bregman divergence was KL divergence. So if you plug those into the above, then you recover the algorithms that we looked at already. But there are many other choices. So you can think about Borg entropy, Zalles entropy, von Neumann entropy. So that's sort of in the, all of these have matrix upgrades. Von Neumann is the matrix upgrade of Shannon. And so there is a whole world of choices to play with that might give you different trade-offs that we'll discuss right next. And there are interesting connections to something called continuous exponential weights, which I also just want to point you to. I'm not going to say anything about them. All right, so what can you show for this FTRL or mirror descent? So let me just focus on one theorem. It's for a kind of a slightly fancy algorithm called ADA FTRL. And but it incorporates many of the sort of follow-up questions that we were asking before. So let's see. So we're measuring the size of our domain U, but not directly, but with a roundabout trick. We're saying, let's assume that we have a regularizer that's both bounded and strongly convex with respect to some norm of our choice, right? And if you have a norm, you always have an associated dual norm. Okay, and then ADA FTRL ensures the following. So the regret is bounded by the square root of the size of the domain as given by this regularization upper bound times the square root of the sum of all the gradients squared measured in the dual norm. Okay, so now you get to play with these norms, fit them to your domain, and try to see how you optimize this choice. Okay. Good. So let's look at the second bit. quadratic losses. This is actually quite important to get sort of improved regret bounds. If you have any special extra knowledge. So let's look at how that works. So we used convexity in all the past to linearize. We said at any moment that we have to reason about the loss of some other point, we say that's more than the loss of the learner plus a linear contribution. Okay, and we saw that all our methods that work on these gradients are basically pretending that the losses were actually this linear term, right? But in many cases, we may actually know that the losses have curvature. So this linear approximation is lossy, right? So what we'll look at here is how can we represent and quantify that curvature, and how can we efficiently manipulate it, and how much does it help to know about this curvature? Okay, so here's how we quantify and reason about curvature. We're going to say, let's assume that in every round, there is some matrix that we know, maybe after the fact, that's okay. It's a PSD matrix, such that the loss of any point u is more than the linear approximation that we saw previously, plus a quadratic term. So this is a quadratic in u, which makes this a stronger lower bound than the convexity lower bound. Okay, and let's call this whole thing the quadratic of u, because we will need that next. So that's the quadratic approximation that we use as a lower bound on the loss of any other point. Yeah, maybe it's important to point out, if you plug in here WT, you see that you get WT here, 0 here, 0 here. So this quadratic is tied in WT, and this assumption says at any other point, it's a lower bound. Okay. So what are the important instances of this scheme? The first is if you think about like target shooting, telecommunications. In many cases, you have to position and you get the squared distance from some target point. Maybe this is your receiver and this is your antenna. In any case, the squared Euclidean norm satisfies this assumption with the matrix being an identity. Okay, so that's very nice and simple. And more generally, you can think about strongly convex loss functions that have this with a scaled identity. That's basically the definition. Okay, so that's one class. M is roughly an identity. The other important class is linear regression and friends. So linear regression is itself a square. But if you look at the matrix that sits in there, it's the feature vector outer-producted with itself. Right? So that's a rank 1 matrix and not a full rank matrix. And the class of X-concave losses all have a very similar feature, namely that this assumption holds for a matrix that is rank 1, but now based on the gradient itself. Right? If you haven't seen X-concave, then don't worry. It's some class of losses, and I'm going to show that. I mean, linear regression is basically the important example there. Okay, so what is the algorithm for dealing with these quadratics? We have to somehow incorporate this extra curvature in our iterates. And the way we'll do it here is an algorithm called online Newton step. And the way I wrote it is the variant that looks like FTRL. So the iterates that we will produce is the minimizer of the quadratic lower bounds and a starting regularization, which is just the square norm. Okay, so what is the advantage of doing that? So the cool thing is that computing this iterate is just minimizing a convex quadratic. Okay, and if there wouldn't be the restriction that you have to play in U, then there would be a closed form solution. We would just invert the matrix, multiply it by the linear term, boom, that's our answer. If we need to project, then sometimes it's closed form, sometimes there's a 1D line search, Sometimes it may be more complicated, but that can also be done. Okay, so what do we get in the end? If your matrix is a scaled identity, the whole procedure is still D operations per round. So same as online gradient descent. And if it's rank 1, then we can do some rank 1 update tricks to compute these iterates in order D squared per round. Right? And in both cases, there is the projection, but that's sort of an orthogonal thing. You have to deal with that. If you're unlucky, that might cost you a D cubed, but sometimes it's just linear. It depends a little bit on the case. Okay. So what can we show about online Newton step? Well, it is again different for the two cases. If your scaled identity that's strongly convex, the regret is only a logarithm in T. So that's much, much better than a square root. And the algorithm actually looks like online gradient descent, except with a very specific decreasing step size. That's often how this result is presented. But I think this is more revealing in where it comes from. And in the exconcave case, where you are some rank 1 version of the gradient, then this scheme guarantees a regret of at most D log T. Right, so it's still in the log T regime, but somehow here you're only learning about one direction at a time. So you have to pay the learning overhead D many times. I guess that's one way to think about it. Okay. So what was sort of interesting and what was happening? These convex quadratics are very nice in that you can sum them over rounds and represent them as sort of a single statistic that doesn't grow in size with the number of rounds, right? So that's nice. We can summarize the coefficients of the sum in a single matrix, and that makes that the runtime stays independent of the time horizon. Good. We saw that curvature gives a huge reduction in regret, goes from a square root to a logarithm, so that's great. So learning is much, much easier, and you can be much more successful in these curved regimes. And then if you're worried about runtime, which I guess in some sense you should be sometimes the dimension is just millions and then D squared is sort of horrible. There is a very nice way to interpolate and treat some of the dimensions as special, maintain matrix-like quantities for them, and throw away others. So that's called sketching. And this allows you to trade off both in the runtime and in the regret and get sort of a nice balance between the two. All right, finally, I want to conclude with 3 applications. So this is going to be, in some sense, very fast. So first application is offline optimization. So we've been doing things online with a varying function, a different function every round. So what if we want to solve the following problem? We have, let's say, gradient access to a fixed function, and we want to find a near optimal point. Okay, this is a question that maybe you encounter at least once a day. So how can you do that with online learning? Well, in some sense, it's quite a natural trick. You say, let's run online gradient descent, and let's feed it the same function every time. Okay, so if I then write down my regret bound, I see that the sum of the losses with the same f minus t times the loss of the best point is bounded by my regret bound of GD square root t. Okay, if I then divide by t and move the average outside of f here inside of f, I find that I have a point, namely the average of the iterates, that looks that is very close in value to the minimizer of my f, up to something that scales as 1 over square root t. Okay, so that means that if you want an epsilon suboptimal point, you solve for this equals epsilon, and you find that after roughly something over epsilon squared rounds, you have that proximity in function value. Okay, so now you can ask, yes, but I can also use some other optimizer, so why would I do it this way? And I think we saw some answer like this in the previous talk, Because is this really using all that we know? Maybe if you use it maybe better, that there is a single function, maybe you can get a better speed. Yeah, but you can turn that around as well and say, what if my assumptions are sort of not quite true? If I have a robust thing like what's written here, it might still work. So for example, a thing that I encounter quite a lot is that I have a fixed function, but I need to learn it. So I have iterates that converge to this fixed function, and I want to optimize with this approximate f's. Okay, so that this scheme can still do something for you if you're in a world like that. Okay, second application. What if I have stochastic data? Okay, so let's rephrase that in the online convex optimization language. That means I'm going to give myself access to a training set. So that's a bunch of functions and a test point, and they're all drawn IID from some unknown distribution on loss functions in this case. Okay, so what do I want? I would like to look at the training set and output some point, and I would like this point to do very well on a fresh test point from the same distribution. So that's called generalization. I would like my estimate to behave like the point that optimizes the expected loss. Okay, so what can you do? It's somewhat similar to what we did before. You run your online learning algorithm on the training set. So that's the functions f1 through ft. And that will give you some iterates, w1 to wt. Then you output the average iterate as your candidate for this point. And you can show, it's again some manipulation with IID, swapping some things around, invoking convexity, that the expected difference in expected loss between your prediction and the optimal point goes down as the regret bound divided by t. Okay, so the expected loss on the test point, basically if you run online gradient descent, will go down as 1 over square root t. So again, that gives you an idea for how many data points you will need to get a certain optimality on your generalization. Okay, last application, and we also saw an example of that, which is great, in Mendy Wang's last set. So this is about solving games, and for us, let's think of very simple games where we have some objective function, let's call it gxy, that says what is the payoff to player 1 if player 1 is playing X and player 2 is playing Y. Okay, so this is a specification of the winnings of player 1, and that's also what player 2 is losing. Okay, so if we have a function like that, we can think of a game where player 1 plays X, player 2 plays Y, and we look at what they can achieve. So if player X goes first and Y goes second, player X can achieve this. And if they change orders, player Y can achieve that. And for convex concave functions, there are minimax theorems that say these two things are the same. And let's call that quantity the value. So that's what happens if both players play optimally. The value of the game is V star. Now you can say, what if they play slightly suboptimally? Because we're going to try and find some good candidates X and Y. So if we allow ourselves a little epsilon, we can say that a pair of points X and Y is an epsilon saddle point if either player, by playing either X or Y and incurring the optimal response, is at most epsilon away from V star. So that's an epsilon saddle point. And the question is, how would we find an epsilon saddle point? So I'd like to compute this X bar, Y bar. Right? And the idea is, well, we want to learn So let's play a regret minimization algorithm controlling X and another one controlling Y. And let's have them interact against each other, updating their internal state from what they see in each of these interactions. Okay, so how does that look? We do T-many rounds. We ask each of these algorithms to play a candidate X and a candidate Y. And then we feed them as the loss function the quality of the other choices for X if we fix the Y that we got. And for the Y player, we give it the quality of all the other choices for Y if we fix the X that we got. Okay. And then at the very end, we output the average iterate for both of these players independently. All right. And if we assume that these players have regret bounds, let's call that Rx and Ry. So this would be what it means to be a regret bound. Then the theorem is that these iterate averages, X bar and Y bar, are a saddle point with quality the regrets over T. Right? So that could be, for example, again, a 1 over square root T quantity. Okay, this is the proof, but I don't want to go into it. I just want to appreciate how short and symmetric and elegant it is. But let's not worry. All right, so what did we see? So we looked at online learning for the full information setting. We saw that we had these powerful results, these adversarial black box regret guarantees. And we looked at some applications building on top of these guarantees, getting results in optimization, statistical learning, game theory solving, and of course the original interaction itself. Now I just want to point at a few things that I left out and that I think are cool. So just to give you sort of a very quick sense of what else is out there. So you may want to think, what really should control the hardness of my game? We saw, for example, this square root T, but is that really what I want? Maybe I want to introduce some other notion of hardness of the sequential interaction. And there are many proposals for that. First order, second order. Yeah, these are all cool. You can say, well, if my algorithm isn't in a worst case setting, so there is no opponent, it's actually a distribution instead, maybe it should learn better or faster if that happens. Can it figure that out by itself and do the right thing? Something called optimism, which is what if I can predict the gradient? Can I learn faster? The answer is yes, and it's a beautiful theory. This was the question from Discord. What if I don't want to compare to a single action? What if I think that a sequence of changing actions would be much better? So then you get into bounds for non-stationarity, tracking, or dynamic regret, adaptive regret. There are all sorts of things in this space. And finally, what if I don't have a convex function? Can I do something? And the answer is, well, there are all sorts of things just outside. You can, for example, assume is some reduced version of convexity, or you can maybe warp everything and look at convexity in a different space. Of course, we would like to understand why these algorithms actually work for example, deep learning. And I don't think this is explaining that yet, but it's sort of a step towards going there. Okay, so thanks a lot.
So Wouter, there's a Discord question that was sort of partly answered by your last section on applications. The question was, in the beginning, you sort of created a hierarchy almost of problems. There's reinforcement learning, there are bandits, then there are full information problems. So the question was about, could you explain the relationship of this tutorial? Like how does it fit in RL?
Right. So one way to look at it is if you take an RL problem and you start stripping it down, right? You remove the different states and reduce everything down to one state, then you still have actions. In RL, you can make these actions, but then the transition would be back to the same state again. So this is very, very trimmed. And if you also assume that somehow you assume you observe the quality of all actions, not just of the action you pick, then you end up in the full information setting. So that means that every solution to a reinforcement learning problem has to have some aspects of the things that I showed you here, because it is sort of a baby instance, right? So that's one answer. And the other answer, I guess, what I try to illustrate with the list of applications is that there are many subproblems that come up in sort of the design of RL algorithms, right? Some of them internally as the engine have to solve a min-max problem. And then how do you solve a min-max problem? Well, actually, that's sort of a separate thing for which you can make an online learning solution to solve that component and then use the answer in your final algorithm for a problem that lives higher up the food chain, let's say. Right, so it's both special instance and tools for all the problems that come up.
Thank you, Wouter. I'll add to that tools are very important. So the expert stuff will actually show up again tomorrow in the morning session in Online Learning Part 2, where we look at adversarial MDPs.
All right. I think I should hand over to Ellen now. If there are any more questions, you can, I'll be around. I'm in the program. You can find me on Discord or just email.
Sounds good. Thank you, Wouter.
Yeah, enjoy the semester.